So, is there any questions before we start and continue the exploration of the standard model? Everything was clear? You know everything about gauge series, the weak interaction? Perfect, okay. So you know more than me now. Okay, so we learn a lot of things, you know. We learn basically how to use dimensional analysis to compute some decay width, some cross-section. And then, of course, you know, you can spend the rest of your life putting the factor of pi, the logs, whatever. Next to leading order, whatever, yes. But here, there are still few points that we are missing. In particular, you know, I discussed this weak current. I tell you that what I've written so far is not totally exact. There will be some more subtleties coming on. And that's what we want to discuss today. We arrive really at the full understanding of these weak interactions. And the first clue that we are still missing something is by studying the decay of the pion. So the pion is a meson, is a composite bond state of two quarks. And it has very strange decay properties. So you have electrically neutral pion, made of a up and anti-up or down anti-down. So that's pi 0. This has very funny decay property. Most of the time it decays into 2 photons. And that's a very interesting quantum field theory chapter related to what is called anomaly. Maybe I will say a few words about anomaly at the end of the lecture on Friday. But there are also electrically charged pion, right? Pi plus and pi minus. So pi plus and pi minus, for instance, is U d bar, right? So it's a composite bond state of 2 quarks, or I don't know. So this is pi plus, or U bar d. This is pi minus, right? Again, remember that the up is electric charge 2/3, the down is minus 1/3, so d bar is plus 1/3. So this is electrically charged plus 1, right? And so if you take, for instance, pi minus, it will decay into an electron on a photon, and it can also decay into the muon on the photon, right? So far it's good. You know, this interaction respects the electric charge. You start with something -1, you end up with something -1. So now the question is, what is the most frequent decay mode? Is it decay? Well, by the way, it cannot decay into tau, right? Because tau is heavier than the pion, so you don't have enough energy or enough mass to decay into tau. So these are the two most abundant decay mode. So then the question is, what is the most frequent decay mode? Does the pion prefer to decay into electron or muon? You know? Any guess? The muon, yes. Why? Why is that? I mean, a priori, it's very surprising. No, it's very surprising because the muon is heavier. I mean, actually, it's not that far. The mass of the muon is not that far from the mass of the pion. So at the end, the phase space is rather limited. And you know, it's a basic principle. Everything you have something which is heavy, it decays into something which is very light, right? So naively, you would say that the pion should decay into electron because the electron is much lighter. So it's basically decaying, you know, into two objects that are more or less massless, right? So now we can try to estimate, right? I mean, estimate this decay width according to the law that we have derived so far, right? So the decay width of the pion, right? Pi minus. So assuming that again the interaction, so the dynamics which is responsible for this decay is again the weak interaction. I mean, here we are making hypotheses, right? So we know we have learned one beautiful fundamental interaction in nature, and we are trying to see if we can explain everything with this interaction. So again, you know, we say that the pion decay should be proportional to G Fermi to the 5th, squared, sorry. And then the mass, the available mass at your disposal to the power of 5, right? So the decay of pi minus into electron and neutrino electronic should be something like mass of the pion minus the mass of the electron minus the mass of the neutrino electron to the fifth, right? While the decay width of the pion into muon should be something very similar, G Fermi squared, mass of the pion minus the mass of the muon minus the mass of the neutrino muon to the fifth, right? So now you want to put a number. So the mass of the pion is about 140 MeV.
It's just the second line of the...
Yes, right, sorry. Yes. I've been tired. He should have told me before, yes. And then it's anti-neutrino, right? In such a way that indeed you respect also the number of fermions. So here you start with something which is actually made of quark. So the number of electrons, the number of leptons, they say 0. So here you want at the end of the day to also have the finite state something which is 0 electron number, right? So the electron number of the electron is +1. The electron number of the anti-neutrino electron is -1. So you respect indeed. So good. I told you I'm really tired, right? Really dead. Okay. Yeah, the mass of the muon is 100 MeV. The mass of the electron is 511 kilo electron volt. The mass of the neutrino, you don't know. Nobody knows so far, but it's very small, right? It's probably less than 1 electron volt, so you can neglect, right? So it's telling you that if you take the ratio now, right? You take the ratio of this, so the decay width of the pion into electron versus the decay rate of the pion into muon should be the ratio of, let's say, here you can neglect, right? I mean, you can neglect the mass of the electron, the mass of the neutrino. Here. So it's proportional to the mass of the pion to the fifth divided. There is always a fine-tuning problem. Right? The most interesting results are always at the edge of the blackboard. I don't know why. Mass of the pion minus the mass of the muon to the fifth, right? So now you put the numbers. So this is what 140 divided by 40 to the fifth. And that's a number which is of the order 500. Right? So the computation is telling you, right, that the pion should decay predominantly into electron 500 times more often than in the decay of the muon. So now you open the particle data book, you know, these things have been measured, and what you find is just the opposite. Right? So that's the theory. Theory is telling you that it's 500, and the experimentalist is telling you that it's something like 10 to minus 4. So there is a big discrepancy. We are missing something. Right? So there are various reasons why maybe it doesn't work. Right? Maybe at the end of the day, these decay are not controlled at all by the weak interaction. Maybe at the end of the day, here you have some hadrons, some mesons, some quarks, so maybe it's a strong interaction which is responsible for this decay. And we haven't learned yet how to compute, you know, the decay width for the strong interaction. So maybe it's wrong. While maybe also, you know, you have to use different G Fermi for electron and muon, right? Okay. We have discovered, I mean, previously that, yes, the weak interaction are flavor universal. They are the same for electron and muon, but maybe, you know, it's also process dependent. Maybe it's true when you are looking at a neutron and muon decay, but maybe it doesn't apply for the decay of the pion. Maybe, you know, when there is something that you don't understand, you say, well, maybe, you know, it's strongly it's strongly interacting series. The pion, at the end of the day, is strong bound state, you know, of two quarks, or maybe there is strong QCD effect there. There is some form factor that I don't know how to compute. I need to do some lattice computation, and maybe lattice will save me. Right? But still, I mean, here you have something like 6 orders of magnitude, and theorists like to understand things very easily. So clearly there is something that we are missing. This something is a selection rules. Selection rules will tell you that, well, actually, yes, you prefer the muon than the decay into electron. Right? So that was a clear indication that so far we are missing something, and we need to understand what is this extra pieces, that will be able to make the theory consistent with experiment. Okay, and actually these things is related to something that I already mentioned yesterday, that the weak interaction are chiral theory. When we looked a little bit at how to embed the quark and lepton into irreducible representation of SU2 cross U1, I told you without any explanation that you put the left-handed chirality into different representation compared to the right-handed chiralities. Right? So this is what we say. We say that the weak interaction are chiral. They are distinguishing the left and the right chiralities of the fermions. Right? And that's exactly what is actually explaining these things. Right? But yeah, it's worth actually coming back to this notion of chirality, right? Because chirality is something very important. Right? The fact that really you have a left-handed electron that behaves at the end of the day differently than the right-handed electron is something very special. It doesn't occur in electromagnetism. In electromagnetism, you are talking about the electron, right? You never, okay, maybe if you're doing optics, you are talking about the chirality of the photon, the chirality of the electron, but you are talking about the electron. While actually, at the end of the day, we have two different objects, two different electrons, the right-handed electron and the left-handed electron. And now we are going to do an experiment, right? Be with me. So take your finger, do a rotation like this, right? Clockwise, and then you're moving, right? You have to continue. It's a very difficult experiment, right? And what you notice now, if you are below your finger, that suddenly your finger is going anti-clockwise, right? It's a change of perspective. Clockwise or anti-clockwise is not an absolute property, of the motion if you can go faster than the particle, right? In the sense that, yeah, if the particle is massless, you can really define uniquely whether the particle is clockwise or anti-clockwise. But if the particle is massive, it means that an observer can go faster than the particle, so at some time you will see it turning clockwise, and sometimes later on you will see it turning anti-clockwise. Right? It means that if a particle is massive, you cannot say whether it's clockwise or anti-clockwise. There is not, clockwise or anti-clockwise, so the chirality of the particle is meaningless. It depends on the way you are looking at the object or looking at the particle. So the conclusion is that, being clockwise or anti-clockwise has a meaning only if the particle is massless. Right? So if you have two different properties for the left-handed and the right-handed chirality of the electron, right? So if there are two different objects, if they transform differently under the symmetry, or if they interact differently with the gauge boson, in principle, you really expect, right, by special relativity, it's telling you that the mass of the electron should be equal to 0. Of course, you all know that the mass of the electron is not 0, right? So you need to add one extra piece, right? One extra piece of information to make things consistent, to give a mass to the electron and still have two different behavior for the left-handed and the right-handed electron. And this extra piece is nothing else than the X mechanism, actually. The X mechanism is what is going to generate the mass for the electron in a way which is consistent with the chiral property of the weak interaction. So what is the X mechanism? The X mechanism is just a way to say that actually the long-distance interaction, the long-distance symmetries are different than the short-distance ones. So you can have a spontaneous breaking of some symmetry. So the Lagrangian, the Lagrangian that describe the physics at very short distances is invariant under the full SU2 cross U1 symmetry. so short distance, or high energy if you want. So Lagrangian is invariant under SU2 cross U1. But the vacuum, so the long distance, the vacuum is actually breaking some of those symmetry. So the vacuum is only invariant under a subgroup of SU2 cross U1, which is nothing else actually than the U1 of electromagnetism. By the way, I mean, in molecular biology, we also know that chirality is really essential for life to emerge, right? I mean, biologists have understood that if you don't have chirality, life cannot develop. Now there is a question, whether the chirality in molecular biology has anything to do with chirality of the weak interaction. That's still an open question a priori, right? So maybe you will be able to answer this kind of question at some point. Okay, what else? Yes, so now we want indeed to see that the puzzle with the pion decay can be understood really by relying on this notion of chirality. The fact that the weak interaction are chiral will explain indeed that the pion decay predominantly into muon and not into electron. And for that, we can simply look at the decay of the pion. So you will go into the rest frame of the pion. Right? So we will decay, let's say, into a lepton and the antineutrino associated to the lepton. Right? So it's a rest frame, so the two daughter particles just have opposite momentum in this rest frame. And now the pion is a scalar field, so it's spin zero particle. So this means that the spin of the lepton and the neutrino should also be opposite to each other. Right? So the spin, okay. So this one arrow is just the momentum, and the double arrow is just the spin. Right? So now, yeah, that's something which is maybe not obvious, but the neutrino only have one chirality. That, I mean, what has been observed is only left-handed chiral neutrino. So it means that the antineutrino is right-handed chirality, so the spin should be aligned with the direction of the momentum. So that's why here, if the antineutrino is going into this direction, the spin should be aligned with this momentum. And now since, the spin of the lepton should be opposite to the spin of the antineutrino, it means that necessarily here, the spin of the lepton should also be aligned with the momentum of the lepton. It means that here, the lepton should also be right-handed. Right? So the lepton is right-handed chirality, right-handed chiral, whatever. And now, as we saw when I gave you this transformation property of the various particle, right? We have actually seen that the lepton actually interact with the W only if there is left-handed. The right-handed chiralities of the lepton were always singlet under SU2. So singlet means that they don't interact with the W. Right? So since here you need a right-handed lepton, means that you cannot get it directly from the decay of the W. Right? I mean, here again, the assumption that we are making is really that the decay of the pion is coming from the weak interaction. So it's coming due to the exchange of a W. Right? But the W is producing only a right-handed electron or a right-handed muon, a left-handed electron or left-handed muon. Right? So in order to get now a right-handed electron or muon, means that you need to pay a price. You need to flip the chirality. And what is flipping the chirality of the lepton is simply the mass, right? Because in the Lagrangian, if you're writing the mass term for the lepton, is always mixing the left-handed chirality with the right-handed, right, plus complex conjugate. So it's really the mass, as we have seen here, right? It's only the mass which is flipping the chirality of the particles. So here, if you want really to obtain a right-handed lepton, you need to pay a price which is actually proportional to the mass of the lepton. If the lepton is massless, it cannot flip the chirality, and here you will necessarily end up with a left-handed lepton. Right? So what does it mean? It means simply that the amplitude for this process has to be proportional to the mass of the lepton. So that's really this selection rules that we are missing before, right? Here, when we say that it was proportional to the fifth power of the energy, we were missing this fact that the amplitude has also to be proportional to the mass of the lepton. So now we can repeat the same exercise, right? Including now the selection rules. So we say that the decay width of the pion into lepton, antineutrino lepton, should be proportional to G Fermi squared. The amplitude is proportional to the mass of the lepton. So the width will be proportional to the mass squared. And then you need to add 3 power of the energy. So the mass of the pion minus the mass of the lepton to the cube, right? Right? In such a way that now when you compute the ratio of the decay width of the pion into electron antineutrino electron over the decay width of the pion into muon anti-muon neutrino is actually proportional to the mass of the electron squared times the mass of the pion minus the mass of the electron cube divided by the mass of the muon squared, mass of the pion minus the mass of the muon squared. Right? So now is what? It's 500 kilo electron volts, so it's 0.5 GeV squared, MeV squared, times 140 MeV cube divided by 100 MeV squared times 40 MeV to the cube, right? And this is approximately this 10 to minus 4 that were expected from experimental data, right? So you really see right here that it's really important to understand the symmetries and the selection rules to really be able to compute properly this decay width. Well, if the particle is massless, I mean, since the weak interaction are chiral, so the W is talking only to the left-handed chirality, and the particle is massless, it cannot flip its chirality, right? So you can never obtain a right-handed lepton. So it means that here you cannot decay into a lepton which is massless, right? At least not with a weak interaction.
This that you have mentioned of the mass term flips
the chirality.
The
yes.
chirality. This is something that depends on how we are representing the fermions. I mean, if we are using Dirac or Weil or Majorana representation.
Yes, so that corresponds to what is called a Dirac mass term. So the fermions are just embedded into Dirac representation. Indeed, you also have a Majorana representation of the Lorentz symmetry, and for the Majorana fermions, you cannot define actually chirality. So, but you are right that in a sense, I mean, in principle, for some of the fermions, in particular, particular for some of the neutrino, not the electron, not the neutrino of the standard model, but sometimes you introduce some right-handed neutrinos. The right-handed neutrinos don't carry any charge; they are fully neutral under the standard model gauge group, and this allows you to write a Majorana mass for this right-handed neutrino. And in this case, indeed, I mean, the Majorana fermion, in a sense, has no chirality. But here, the mass of the electron actually is a Dirac mass term and is really mixing the two chiralities, and the same for the muon.
But what would we expect if we would like have chosen the value representation to?
I mean, it's independent of the representation. The point is that you cannot have electrons that are Majorana particles because they are electric charge, right? Okay. So only electrically neutral, I mean, only fully neutral object can be Majorana fermions. So you have no choice there.
Could you explain better the difference between helicity and chirality? Because helicity is very intuitive because it's just comparing the direction of spin and linear momentum. Of course, it's not Lorentz invariant, but chirality for me always seems so mathematical, but I can't imagine, you know?
I mean, there is one which actually commutes with the Hamiltonian, so it's really well defined, and the other is not. I never remember which one is which, but chirality or helicity. But yeah. Well, I mean, the pion decay constant is just the fact that, again, the pions are made of a quark and an antiquark, and the pion decay constant is just a measure of this thing. So it is just measuring the amount of energy, the binding energy between the two quarks. Right?
Okay, thank
you. So it doesn't really appear here in this decay because those decays are fully controlled by the weak interaction at the end of the day.
Okay, thank you.
Are you going to expand a little bit more on how the pion actually decays? Because I couldn't understand, like, if it decays with the weak interaction, and the weak interaction only couples with the left-handed fermions, how a right-handed lepton is coming out?
In a sense, I mean, the answer to this question, this being left and right-handed is not a well-defined concept in the Hamiltonian. So, you have to pay a price to basically flip the chirality, and this price is proportional to the mass of the particle. So now, I mean, okay, here, if you just use dimensional analysis to do this computation, now you can, write down all the Feynman diagrams, the Feynman rules, you do all what you have learned in quantum field theory, and you will recover exactly this property that it has to be proportional to the mass. The amplitude has to be proportional to the mass. But again, you understand very easily simply by this symmetry argument. Right?
Okay, thank you.
So at the end of the day, I mean, why the mass appears here, when you are doing your Feynman computation, is simply because you have the trace of the gamma matrices, and some traces are zero, some traces are non-zero if you have enough gamma 5 matrices in the traces. But the deep reason is really this one. It's just conservation of spin, and the fact that if you want to flip the chirality, you need to pay a price which is just proportional to the mass. Okay? Good. Okay. So what else? Yes, so now we are here introducing this X mechanism, at the end of the day to explain how to generate the mass to the electron. Right? So you understand here, you can understand easily here that having a mass again is not directly compatible with a chiral property transformation of the lepton. Right? So if the left-handed and the right-handed chiralities of the electron don't transform in the same way, the mass term is not invariant. Just look at the hypercharge that we identified yesterday. The hypercharge of the left-handed electron was 1/2. So the anti-electron is -1/2. And the hypercharge of the right-handed one was -1 or +1, whatever. -1, I think. So clearly here, this is not invariant under the U1 of hypercharge, right? So the mass term by themselves are not things that you can write in the Lagrangian, because the only thing that you can write in the Lagrangian are some interactions that are fully invariant under the full symmetries. That, you remember, that was the first principle, right? We are trying to write objects that are invariant under some symmetries. Lorentz symmetry, so this is Lorentz invariant, no problem, but this is not invariant under the gauge symmetry. So this is not invariant under U1 hypercharge. This is not invariant under SU2, because SU2, if you remember, the right-handed chirality was singlet under SU2, and the left-handed chirality were part of a doublet. So you cannot construct something which is invariant if you have a doublet and a singlet. So you need to do something else to make the Lagrangian invariant under the full symmetry. And the trick that people have proposed is actually to introduce a scalar field, the X field, which itself transforms under SU2 cross U1. Right? So you introduce the X field, H, which is a doublet under SU2, and he has an hypercharge that we're going to compute in a moment. Right? So it's a doublet under SU2. Right? Let's say hypercharge that we are going to compute. So it's a doublet, so it's a scalar, a complex doublet. So you can write something that will become evident in a moment, H plus and H0. So there is an upper component and a lower component. And here I anticipate actually that this will be the electric charge of those components. Yes. So now the idea is actually to see this mass term. Instead of having a mass term, it will be simply coming from an interaction with the X field. So you have the left-handed doublet, that contains the neutrino electron and the electron. You have the X field, so now you have two doublets, and out of two doublets, you can actually construct a singlet under SU2, and this we will multiply by the right-handed electron. Right? So this is a doublet under SU2. And you will do the same thing for the quark. So you have the up quark, the down quark, the left-handed chirality. You have the X, and then upright. And the same thing here, up, down, left, H, down, right. So, okay. So for SU2, that works. Now we need to find the hypercharge in such a way that all this interaction can be invariant. And the subtlety is that at some point I need to introduce a complex conjugate, H dagger. Right? So for a doublet of SU2, the complex conjugate is also a doublet. So what we say is that the fundamental representation of SU2 is actually pseudo-real, because its complex conjugate transforms actually in a way which is equivalent to the fundamental representation. This is not true for SU3. The triplet representation is different than the anti-triplet. But for SU2 is exactly the same thing. Okay, so now I don't remember the hypercharge that we have introduced for the neutrino and the electron. It doesn't matter because we are going to recover those hypercharge. Right? I told you that the electric charge is just T3 plus the hypercharge. So now we want the neutrino to have an electric charge 0. T3 is plus 1/2, so it means that here the electric charge, the hypercharge is minus 1/2. Now I won't put the bars, right? to be something to obtain something which is invariant under Lorentz transformation, I need to take a fermion bar times a fermions. Right? That's the only thing that is invariant under a Lorentz transformation. So now, if I'm looking at the hypercharge of this object, so here I say it's 1/2, so it's -1/2, no, +1/2. Here it's -1. So I need that the x is -1, no, +1/2, right? In such a way that this object is also invariant under U1 of hypercharge. Clear? The same is also true here. So the electric charge of the up is 2/3, right? So the hypercharge is equal to is equal to 2/3, yeah. 1/6, right? 1/6 plus 1/2 is 2/3. 1/6 minus 1/2 is -1/3. Means that the hypercharge of the left-handed quark doublet is equal to 1/6. So here it's bar, so it's -1/6. Here is h bar. So h has hypercharge 1/2. So here it's -1/2. And the hypercharge of the right-handed up quark is 2/3. Right? And again, -1/6 minus 1/2 plus 2/3 is equal to 0. So this is also invariant under hypercharge. Right? And the same is true here. Right? So here it's also -1/6, 1/2 minus 1/3. So here we have been able to write really some interaction between the Higgs and the lepton or the quark that are fully invariant under Lorentz transformation and fully invariant under SU2 cross U1. Okay? So now remember also that we don't have a single electron. We have the electron, the muon, and the tau. So there are 3 families, 3 flavors of lepton and 3 flavors of quarks, right? So it means that here actually there is index I and J, which are the flavor index, I and J, I and J. And here we can introduce in front of that some numbers that we call the Yukawa interaction that are matrices in flavor space, IJ, Y up IJ, Y down IJ. We can also look at what is the mass dimension of those objects, what is the mass dimension of those interactions. Right? So remember here we have a fermion, a scalar, and a fermion. So the mass dimension of a fermion is 3/2, so 3/2 plus 3/2 plus 1, the mass dimension of a scalar. So this is mass dimension 4. And I told you that the Lagrangian need to have mass dimension 4. So the mass dimension of this Yukawa interaction is equal to 0. Right? So the mass dimension of up, of the Yukawa of the up, the down on the electron are exactly 0. Okay? So what is the next step? Well, we have a scalar field. So scalar field doesn't transform under Lorentz symmetry. Right? I mean, that's what we have learned in the first lecture. Scalar field don't transform under Lorentz symmetry. So it means that in the vacuum, you can give a non-zero value to the field, and this is still invariant under Lorentz symmetry. So the vacuum can respect the full Lorentz symmetry, even if the field acquires an expectation value, a non-zero expectation value. So that you can do with scalar field. You cannot do that with fermion because, I mean, as we have seen, the fermion are not invariant under Lorentz symmetry. So fermion cannot acquire an expectation value. The same is true for the gauge field. But the scalar field can do that. So that's the only object in nature that can fill the full universe while being consistent with Lorentz symmetry. So that's exactly what happens, in the early times of the universe. 0.1 nanosecond after the Big Bang, actually the universe fills itself with a non-zero expectation value with the X field. So what is the dynamics of these things? I mean, that probably Kfir is going to tell you a little bit about it later today. It's a phase transition, so nobody really understands what is the dynamics of this phase transition, whether it proceed by producing bubbles, and then the bubble expand and fill all the universe, or whether it's a continuous phase transition, a second-order phase transition. Right? In the standard model, it looks like at the moment, if you compute the dynamics, it looks like it corresponds to second-order phase transition. But nobody knows at the end of the day if the standard model is really the full story, right? Probably there is new physics, maybe there is some scalar field. Somebody wanted to introduce some singlet scalars, and the singlet scalar can totally change the dynamics of this electric phase transition. So you can indeed have some bubbles. And if you have bubbles, it's very exciting because the bubble can collide, they can produce gravitational waves, right? So by looking at gravitational waves, that are remnant of what occurs 0.1 nanosecond after the Big Bang, maybe you will understand exactly the dynamics of this phase transition. Okay, so yes. So we have introduced this scalar field, so we know at the end of the day that you want to give a vacuum expectation value to this scalar field. And that's exactly what is going to produce the mass of the electron, the mass of the quark, and also the mass of the W and the Z. Because at the end of the day, I got a nice story. I was able to reproduce this 4 Fermi interaction if I had introduced a mass term for the W. But I also told you that the mass term for the W is not invariant in the gauge symmetry. Right? So there is a little bit of contradiction in what I'm doing. But we are going to see again that giving a vacuum expectation value to the X field actually generates the mass of the W in a way which is consistent with the symmetry of the Lagrangian. Right. So we have introduced a scalar field, the X field, and now we need to look at the kinetic term for this X field. Right? We need to write a kinetic term for the X, which is invariant again under SU2 cross U1. But that's easy, right? The only thing that you need to do is introduce this covariant kinetic term. So you replace the space-time derivative by the covariant kinetic term that introduces some interaction of the X field with the gauge boson. And since we know how the X transform under SU2 cross U1, we can easily write explicitly this covariant derivative. D mu H, just the usual space-time derivative, minus I, G, which is the gauge coupling of SU2. Then you introduce a gauge boson associated to SU2. So W mu A, the generator of SU2, which are the Pauli matrices divided by 2 for a doublet representation, times H. Okay. So that's just because you want the X field to transform as a doublet under SU2. Right? So you introduce the generator. So this is what I called A mu A, or A mu. Before, that was a matrix, right? So now I can write explicitly this matrix because I know that I'm dealing with the SU2 group, and the generator should be the generator for the fundamental representation, or the doublet representation. And we have also noticed that the X field should be charged under the hypercharge. So there is an extra piece, minus I, G prime, B mu. The hypercharge of the X was equal to 1/2, minus 1/2. Let's say plus 1/2 B mu times X. So this WA are the gauge boson of SU2. And this is B mu is a gauge boson of U1 hypercharge. Sometimes we say SU2 left because the SU2 is acting only on the left-handed chiralities of the quarks and the leptons. good. So now the X field itself will acquire an expectation value, right? And for some reason that I'm going to explain, the expectation value can be written like this. So it's only, let's say, the lower component. Is something weird, then you should find +1/2. Okay. Maybe a reverse H with H dagger, right? Maybe you should put H dagger here. So you, I know, H is +1/2. Right? Okay, so that's fine. +1/2. Yeah, so what is the electric charge of the upper component, right? So I have a upper component and lower component. What is the electric charge of this object on top of the doublet? The electric charge is again T3 plus the hypercharge. Yes, so there is something weird in my normalization, right? That's not the usual normalization that people are using. It doesn't matter. But so here, the upper component should be +1/2 here. And if I change H into H dagger, the hypercharge will be -1/2 in such a way that the upper component has an electric charge 0. So Q, the electric charge of this upper component is 0. No, it's +1. Sorry. And this, the electric charge of the lower component is 0. That's it, right? +1/2. So the upper component is +1/2, +1/2, so electric charge +1, and the lower component is -1/2, +1/2, which is 0. Okay, so everything is consistent. I didn't do any mistake, sorry. So which is good, right? Because if you have an object that doesn't carry an electric charge, you acquire an expectation value. And since this object doesn't transform under electromagnetism, because its charge is 0, it means that this expectation value fully respects electromagnetism. It doesn't transform under electromagnetism. So this object is invariant under electromagnetism. And here, this object is not invariant under electromagnetism, but its expectation value is 0. So it doesn't break. Nothing is breaking electromagnetism. So that's why this expectation value of the X field actually break SU2 cross U1 down to U1 of electromagnetism. That's the symmetry that remains unbroken in the vacuum. So this VAV, the vacuum expectation value of the X field, is invariant under U1 of electromagnetism, right? So SU2 cross U1, which is the symmetry of the Lagrangian, SU2 cross U1 is broken into U1 of electromagnetism. That's a spontaneous breaking of a symmetry. This is the symmetry of the Lagrangian, this is the symmetry of the vacuum. So this is the symmetry of the short distance physics, this is the symmetry of the long distance physics. Right? So now what we want to do is actually rewrite, the Lagrangian in the vacuum. So first of all, we will assume that you are at energy, let's say, below the mass of the X field. So you can really replace the X field by its vacuum expectation value, and then we will look at the perturbation around it. So what we are going to do now is insert this vacuum expectation value in the Lagrangian, in particular in the kinetic term of the X field. And here we see immediately something happening, right? So if the X now is not a field, but is just a vacuum expectation value, this kinetic term for the X field actually is a term quadratic in the gauge boson. Because you have one gauge boson here, one gauge boson there. So it's really a quadratic piece in the gauge boson. And the quadratic piece is nothing else than the mass term. So this kinetic term of the X actually is actually generating the mass term for the W and the Z. So that's what we are going to derive here explicitly. Right. So in the vacuum, let's rewrite this covariant derivative. D mu h. So h, X field itself is just constant everywhere, so it doesn't depend on space-time. So the derivative on this expectation value is 0, right? So this is 0. Minus I, j. So now I need the Pauli matrices. So sigma 1 is 1, 1. Sigma 2 is 1 minus I minus I. And sigma 3 is 1 minus 1, right? It's diagonal, is a diagonal matrix. So it means that here, this W mu A sigma A over 2, so we'll put this factor 2 in front of it. This is W3 mu minus W3 mu. Is W mu 1 minus I W mu 2. W mu 1 plus I W mu 2, right? And this is acting on the vacuum expectation value. So 0 V divided by 2. Then I have the same thing, minus I over 2 G prime, B mu, and so this is diagonal, B mu acting on 0 V square root of 2. So this square root of 2 is just a normalization convention, doesn't matter. Okay, so let's see what I get. So here I get a vector again. So it's 0, 0. Minus I over 2 G W mu 1 minus I W mu 2 V over square root of 2. Here I don't get anything. And here I get minus plus I over 2 G W mu 3 minus I over 2 G prime B mu times V square root of 2, right? So that's, in the vacuum, that's the expression of the covariant derivative of the X field. And now in the Lagrangian, I need to take the squared of this. So in the vacuum, the Lagrangian contain actually, so it's dagger of this times itself. So it will be G squared divided by 4, W mu 1 minus I W mu 2 times W mu 1 plus I W mu 2 times V squared over 2 plus I 1/4 G W mu 3 minus G prime B mu squared V squared divided by 2. So as promised, I mean, this kinetic term of the X field actually contain some mass term for the W and the Z. Right? I can identify what the W and the Z are directly here. Right? This Lagrangian. If I call Z, let's say, Z mu will be this particular linear combination. So J W mu 3 minus J prime B mu. And I want to do a rotation, so I need to normalize these things by G squared plus G prime squared. Right? So that's a new gauge boson. And then the orthogonal linear combination that will become the photon, actually, is just this one, G squared plus G prime squared times G prime W mu 3 plus G B mu, right? So these are just two orthogonal linear combination of W3 and B. And here you see directly that the Lagrangian now, the Lagrangian will contain a piece which is what? 1/4, 1/8, sorry. 1/8, G squared plus G prime squared, V squared times Z mu, Z mu. Right? So that's exactly a Z boson, right? With a mass for the Z. The mass of the Z squared is equal to 1/4 G squared plus G prime squared V squared. Right? So you have identified the mass of the gauge boson, which is simply the vacuum expectation value of the X times the gauge couplings. So that's for the electrically neutral sector. So here the B doesn't carry any electric charge. The same is true for the W3. So those two gauge bosons actually are electrically neutral. So that's why we say that this is really some neutral current, and this is just electromagnetism. As we know, this is also a neutral current. Right? So those two gauge bosons mediate some neutral interactions. And then you have the W plus and W minus, which are just those linear combinations. 1/2, W mu 1 plus or minus I W mu 2. Right? And you can check that actually those two things actually indeed carry an electric charge which is plus or minus 1. Right? And then it means that the mass term now is 1/4 G squared, V squared, W mu plus W mu minus. Right? So the mass of the W squared is 1/4 G squared, V squared. And the mass of the photon is exactly equal to 0. Right? Here there is no mass term for the photon. So the photon remains massless, which is not a surprise. It's not a surprise because U1 of electromagnetism is an unbroken symmetry in the vacuum. Right? So every time you have an unbroken gauge symmetry, you do expect the gauge boson to remain massless. Okay. So that was for the gauge sector. So we have seen exactly that the expectation value of the X generates the mass for the gauge boson. And now we can check here also what is happening for the fermion. Those Yukawa interaction will generate some mass term for the fermions in a similar way. So you replace, again, in the vacuum, you replace the X field by its vacuum expectation value. Right? So here you replace it by 0 V divided by square root of 2. Same here. And here you do the contraction, and this will generate YE IJ. And here you will pick up actually the electron component. So it's EL bar I, E right, J, V divided by square root of 2. Here, since it's a dagger, here you will pick up actually the upper component, Y up IJ, up left I, up right J, V divided by square root of 2, plus finally Y down IJ. Now it's H, so again it's the lower component. So just the way you contract, two doublets, right? Sometimes you take the lower component or the upper component, depending if it's a dagger or not. Right? So here it's DLIA, D right J, V divided by 2. Right? And now you see that what you have is nothing else than the mass for the electron, the mass for the up quark, and the mass for the down quark. Right? Let's say if you don't care about the indices, so if you have a single family, you identified here directly that the mass of the electron will be the Yukawa of the electron, V divided by square root of 2. The mass of the up quark is y up, the Yukawa of the up quark, v divided by square root of 2. And the mass of the down is up down, v divided by square root of 2. Okay? So really the X mechanism allow you to generate the mass for the gauge boson and the fermion at the same time, in a way which is fully consistent with the symmetry. So you start with a Lagrangian which is fully symmetric. You break spontaneously the symmetry by, generating an expectation value for the scalar field, and this gives you directly the mass. So the mass, here was invariant on the SU2 cross U1, and at the end of the day, you get something which is fully invariant on the U1 of electromagnetism. That's why, we can introduce a mass in QED, the mass of QED, because QED is a vector-like series, not a chiral series. So QED doesn't see the difference between left and right-handed electrons. So that's why, nobody bother you, to introduce a mass in QED, because QED is vector-like. So you don't need the Higgs. But the weak interactions are actually are chiral, so they see the difference between left and right. And then, you cannot write directly the mass. You need really to rely on the interaction with the Higgs field to generate those masses. Okay? Good. Okay. Yeah. So that was a vacuum, right? So now we want, yes, please.
So my question is just about the difference between QED and the electroweak sector, because in the electroweak sector, both the gauge bosons and all the leptons acquire mass through Higgs mechanism. But if you just look to QED Lagrangian, there is a mass term for this Dirac spinor.
Yes.
And in particular, this term is not invariant under chiral transformations.
Because QED is not chiral. QED is vector-like.
But
The electric charge of the left-handed electron is the same electric charge as the right-handed electron.
But there is still a mass term, so how do you interpret this mass term that is in QED?
Again, in QED, you can write the mass, and the mass is automatically invariant under U1 of electromagnetism, right? Because look at here, right? You have E left that has a charge, electric charge -1, E right which has electric charge -1, so it's -1 bar, so it's +1, so it's +1 -1, so this is 0. So the mass term in QED is automatically invariant under U1 of electromagnetism. So that's why, you write explicitly in your Lagrangian the mass for the electron. There is no inconsistency. That's something you cannot do for the weak interaction again, because the weak interaction is chiral, so the left and the right don't transform in the same way. So you cannot write directly a mass term which is invariant under chiral transformation.
Okay, thanks.
It's okay? So now the next step will be actually to do X physics, right? Because I have introduced this X field, and I've looked at what is happening in the vacuum, when I've frozen the dynamics of this field. But of course, he has some degrees of freedom also, right? So we want to understand what is the physics of these degrees of freedom. So here, we want to start with a simple counting, first of all, to understand where the degrees of freedom are going, right?
Could be a similar term for right-handed neutrino in that way, the first Yukawa?
So, in the standard model, you only have the left-handed neutrino. So, of course, in principle, you could add, in the big table of the particle content, you can add the right-handed neutrino. And then, indeed, in this case, you could actually write some Yukawa interaction that connect this doublet of the lepton with the right-handed neutrino. With things that you can write. Maybe I'll discuss that later. It's also gauge invariant. And that's the way you want to generate the mass for the neutrino. But if you had a right-handed neutrino, then, as it was discussed, we could also introduce a Majorana mass for the right-handed neutrino. It's another term which is, again, fully gauge invariant. So there are two different possibilities, let's say, to generate the mass of the neutrino. Either you rely fully on this Yukawa interaction, so it's a Dirac mass term after electric symmetry breaking, or you have another component, maybe to the mass, which is the Majorana mass for the right-handed neutrino. So the big difference between Dirac mass and Majorana mass is that the Dirac mass, respects the number of fermions. Here you have fermion minus 1, fermion. So the number of fermions is conserved in those interactions. For the Majorana mass, actually, you violate the lepton number or the fermion number by 2 units. So whether the number of lepton is conserved in the Lagrangian is a question that we don't know how to answer. I mean, we don't know yet, if indeed there is a right-handed neutrino, if the right-handed neutrino have or not a Majorana mass. It's an open question. There are some experiments that are trying, to probe whether the lepton number is indeed conserved or not. There is in particular this double beta without emission of neutrino that is trying to identify the Majorana nature of the neutrino. But so far there is no result to those experiments, so we don't know yet. Now, anticipating also a little bit what I will discuss in the last lecture, actually the lepton number, even if you don't introduce this Majorana mass, the lepton number is violated by what is called anomaly, so by non-perturbative quantum field theory effect. Actually, there is some instanton effect that breaks the lepton number. The same for the baryon number. Baryon number is not an exact symmetry of nature, but the violation of the lepton number is exponentially small. So that's why we haven't seen any big effect yet. Okay? Yes. So let's come back here to the physics of the Higgs boson. At the end of the day, the fluctuation of the Higgs field above its expectation value is what leads to the Higgs boson itself. So the thing that has been observed at the LHC in 2012, right, when Rogerio was there. Yesterday. So, but yeah, before I introduce the Higgs boson itself, want to do a counting of the number of degrees of freedom. Right. So let's remember quantum mechanics. So quantum mechanics is telling you that a particle of spin s, so particle of spin s has 2s plus 1, 2s plus 1 degrees of freedom. Right? That's the first thing that you learn when you're doing quantum mechanics. Probably that's the most important, maybe more important Heisenberg identity, Heisenberg uncertainty, because Heisenberg uncertainty is just it's just classical physics at the end of the day, the wave function. But really what is special about quantum mechanics is this property that the particle of spin s has 2s plus 1 degrees of polarization. But of course, you all have done optics, right? You know that the photon, which is spin 1, has only 2 polarization. So optics and photon physics is already a counter-argument to this quantum mechanics. So does optics violate quantum mechanics? No, because the answer to this is, again, that there is one exception to that, is if the particle is moving at the speed of light, which is not a surprise, because again, combining quantum mechanics and special relativity, as we have learned, by doing this experiment of rotating finger, you see that if the particle is massive or if the particle is massless, they have different intrinsic property. If particle is massless, it always goes at the speed of light, and you can give a meaning to clockwise or anti-clockwise, right? But if the particle is massive, then you can go faster, and then things are mixing up, right? So you are losing, let's say you can lose some degrees of freedom if the particle is massless. So that's why the photon, which is a massless object, clearly, the photon has not 3 degrees of polarization, but has only 2. So massless spin 1 massless spin 1 has 2 degrees of freedom, while a massive spin 1 actually has 3 degrees of freedom. Right? So now, let's count exactly the number of degrees of freedom that we started with. Right? So at high energy, the particle content is the following. You have the X doublet. So the X doublet is a doublet of scalar field. Right? So he has an upper component and a lower component, and each of those components are complex field. So effectively, it contains 4 real degrees of freedom. Right? So this is 4 real degrees of freedom. And then what else do I have? I have the W1, 2, 3, and I have B mu, right? And those fields are massless spin 1 particle. So you have 4 gauge boson, 4 massless gauge boson that correspond to 2 degrees of freedom. So it's 4 times 2 degrees of freedom. So at the end of the day, you have what? 12 degrees of freedom. Right? So now you want to do the counting in low energy. So low energy means after electric symmetry breaking. So in this case, you have the W plus and W minus that are now massive. W plus minus, which are massive spin 1. So you have 2 times 3. You have the Z, which is also massive, so it's 3 degrees of freedom. You have the photon, so gamma or A, depends on the way you want to denote this particle. So now it's a massless gauge boson, right? The photon here remain massless, so it has 2 degrees of freedom. So it means that what was contained in the X doublet now can only be 1 remaining degrees of freedom, right? In such a way that you get 6 plus 3, 9, plus 2, 11, plus 1 is equal to 12. Right? So out of the 4 real degrees of freedom that were contained in the X field, there is only 1 at the end of the day that remained in the spectrum. The other 3 components here, the other 3 real degrees of freedom that were contained in the X doublet actually became the longitudinal component of the W and the Z. Right. So this is what we call sometimes the Goldstone equivalence theorem. I will discuss probably tomorrow what is the physics, what are the interaction of this longitudinal component of the W and the Z, and we will see that you can really understand the physics of those longitudinal degrees of freedom simply as the physics of some component of this X doublet. There's a Goldstone boson because you are breaking some symmetry, right? If you forget about the fact that the symmetry are local symmetry, you can just assume that you are performing the same transformation everywhere in space-time. So the symmetry becomes a global symmetry, and you know that if you break spontaneously a global symmetry, you generate some massless Goldstone boson in the spectrum. Right? So here you have 3 massless Goldstone boson associated to the breaking of SU2 cross U1 down to U1. And those Goldstone boson actually are eaten to become the longitudinal component of the massive gauge boson. Right? So that's the Goldstone equivalence theorem. And we will see some example, right? We see that really this longitudinal component really behaves like Goldstone boson. So it means that they have some interaction that are proportional to the derivative. So they're proportional to the momentum. So some interaction that are growing with the energy. Okay. So yes, so out of these 4 degrees of freedom, only 1 remains in the spectrum after electric symmetry breaking. And this physical real degrees of freedom is what is called the Higgs boson. So this one is the famous Higgs. right? So here you shouldn't confuse this X field and the Higgs boson. Right? Most of the Higgs field are actually something that was already observed by UA1 and UA2. The mass of the W and the Z are nothing else than some component of the Higgs field. The big discovery of LHE was really to identify these additional degrees of freedom. Okay. And a nice parameterization of this Higgs field is simply actually to take the fluctuation of the Higgs field above its expectation value. So this is a Higgs field. Now it's a field. It has 1 degree of freedom. This is a field that depends on space-time. So this is just constant everywhere, and this is a field. So this is a vacuum expectation value, and this is a field. So now we want to see what are the interaction of this Higgs field, the Higgs boson, with all the other particles, with the W, the Z, with the photon, with the quarks and the lepton. Right? But that's quite easy, right? You just need to take the Lagrangian, and everywhere where you add V, you replace V by V plus H. So the Lagrangian was what? The Lagrangian was, let's say, 1/2 mz squared z mu. So now you replace, so this is V squared, so you replace V by V plus H squared, right? The same for the W. The interaction with the W is mW squared, W mu plus W mu minus 1 plus H over V squared. Right. Now the interaction with the quarks and the lepton, let's say, we'll neglect for a moment the various flavor. Right? It was simply the mass of the electron. E right, E left, or E left bar, E left. E right plus complex conjugate. And now this is simply proportional to V, so it's only 1 power of the Higgs field, right? And the same for the quark, right? Plus quarks. Right? So what you notice here, for instance, is that the Higgs boson will couple to the quark and the lepton in a way which is proportional to the mass of those fermions. Here, yeah, okay. Here it's also proportional to the mass squared, whatever. But the interaction of the Higgs field to the particle, to the various particles, is always proportional to the masses of these particles. Right? That's the thing that you may have read in every newspapers in 2012. Probably not all of you were born, but it doesn't matter. You have read all newspaper. And it was said, indeed, that the Higgs coupling are proportional to the masses of the particle. And that's something which is now established experimentally. You can draw a diagram that plots the coupling of the Higgs to the various particles. So the Higgs coupling, let's say, to the particle X as a function of the mass of X. The theory prediction is that everything should be proportional. So the coupling should be proportional to the mass. And we have measured the interaction of the Higgs with the top quark. So it's 1 point here. So with 1 point, it's easy to draw a line, of course. But you have also measured the interaction with the bottom. Well, maybe I should put the bottom here. There is a Z, there is a W. So you here. The bottom is also there. What else? There is the tau. The tau has been measured. There is some indication about the muon. So the tau is also almost on the line. So of course, it's experimental physics, so there is some error bars, right? But all the error bars are consistent with the theoretical prediction. So this is a fantastic plot that we know was made thanks to all this LHE measurement. For the muon now, there is indication that indeed the Higgs coupled to the muon in a way which is proportional, but I mean the error bars are very large, so maybe you don't know yet if you are really on the line. Unfortunately, for the other quarks and lepton, the masses are so tiny that the interactions are very, very small, and you have no sensitivity yet at the LHE to detect and be able to measure those interactions. Okay. And now, you notice that here, there is no, in the Lagrangian, there is no interaction of the X with the photon, because the photon is massless, so its interaction with the X to the X boson is exactly 0 at the classical level. Right? In the same way, there is no interaction with the gluon, so I haven't introduced the gluon yet. I mean, the gluon is just the gauge boson of QCD. Of course, the X boson is not charged on the QCD, so he has no interaction. He has no interaction with the gluon, so the gluon remains massless. Nonetheless, I mean, quantum mechanically, and this is how actually the X boson was exactly produced at the LHE. It's coming from gluon, the gluon that are contained inside the proton. Right? So you have gluon that are inside the proton. So at the LHE, you have a lot of gluon. The gluon actually produce some loop of top quark, and the top quark is interacting a lot with the Higgs boson. Right? So that's the main production channel of the Higgs boson at the LHE. So you start with 2 gluons here, and you produce the Higgs via quantum mechanical effect of a virtual loop of the top quark. And in a moment, or maybe tomorrow, we are going to compute the cross-section associated to the production of the Higgs, just using, again, dimensional analysis. Right? So you don't need, to know exactly how to compute this loop, to take care of the divergences and anything. You can estimate the cross-section just using dimensional analysis. Of course, the Higgs, is an heavy particle. I mean, at the end of the day, something that I didn't mention yet, but the mass of the Higgs is 125 GeV. I will tell you where the mass of the Higgs is coming from. Right? I didn't discuss at all yet the Higgs potential. I just assume that the Higgs acquire an expectation value, but you can explain, or at least parameterize this expectation value in terms of the Higgs potential. And the Higgs potential also generates the mass of the Higgs. And this has been measured. This is something which is not predicted in the standard model. It's just an input, just one parameter, one free parameter that you need to go and measure. And this has been measured 125 GeV. So this is an heavy particle. It couples to light degrees of freedom, so the Higgs boson will decay. Right? And since the interaction of the Higgs are proportional to the mass of the particle, the strongest interaction, the strongest decay, the largest decay width will be into the heaviest particle the Higgs boson can decay into. So it cannot decay into top quark because the top is 173 GeV, right? So there is not enough energy for the Higgs to decay in top quark. And then the next particle that the Higgs can decay into are actually the bottom quark. Right? It cannot decay into 2 Ws either. W is 80 GeV, so 2 Ws is 160 GeV, so the Higgs cannot decay into W, cannot decay into Z. It can decay into a Z which is off shell, but not on shell. Right? So the largest dominant decay mode of the Higgs is actually the Higgs decaying into bottom quarks. BB bar. It can decay into the other quark, into charm, into strange, into tau, muon, etc. Maybe electron also. Right? One thing which is remarkable, and that's something we will figure it out tomorrow when we will be looking really at those interactions in the flavor space. One particular and remarkable thing is that the Higgs interaction are diagonal in the flavor space. So we couple B to B quark, C to C bar, okay, whatever. But doesn't couple bottom with strange. So it's diagonal in the flavor space. So we say that the Higgs doesn't mediate at 3 level, doesn't mediate flavor changing neutral current. So F, C, and C. flavor-changing neutral current are absent from the X interaction. This is also absent, actually, that's something we should discuss at some point, is also absent in the interaction of the Z. The Z interaction to the quarks and the lepton are diagonal in flavor space. And that's, I mean, a remarkable property, you know, of the structure of the standard model if you want to do any flavor physics. You know, flavor physics is just looking at the decays of the various meson and baryons that are, you know, non-trivial transformation on the flavor symmetry. You know, and you can really obtain, I mean, important constraint on any physics beyond the standard model, because this is highly non-generic. You know, it's highly non-generic that you have physics that are diagonal in flavor space. Here it's just due to the fact that, you know, you have interaction with a single power of the X field. You couldn't write any other interaction that are, you know, of mass dimension 4. But if you are interested of mass dimension 6, for instance, nobody prevents you to add 2 extra power of the X field, right, in the Lagrangian. Okay, this is a non-renormalizable interaction, but who cares at the end of the day, right? And here, now, if you have 3 power of the X field, actually, generically, you will expect, actually, that the X interaction are non-diagonal in flavor space. Right. So that's something we will discuss in more details tomorrow, really what is the flavor structure of these things. But one important thing is really that the X decay dominantly into a pairs of bottom quark, BB bar, and there is no flavor-changing neutral current. So the exercise for tomorrow is to compute the cross-section for the production of the X and to compute, well, this decay width, right? So you want to compute the lifetime of the X boson. So you will find at the end of the day that the lifetime of the X is something like 10 to minus 21 seconds. So it took a long time and a lot of effort actually to produce the X boson, and the X boson decays immediately. So nobody has actually seen the X boson, right? The only things that we have seen are the decay product of the X. So these pairs of bottom quark or whatever, we will study all possible decay mode of the X. So it's like dinosaurs. Nobody have seen the dinosaurs. We have seen only the decay product of the dinosaurs, all the bones, right? That's exactly the same thing for the X. Okay, so we'll stop here today. Thanks.
Okay, thank you, Christophe. So questions for Christophe? Yes?
I have two questions. The first one is about the degrees of freedom of massless particles. What happens if we have a massless particle with higher spin, like, for example, the graviton?
Well, I mean, in the standard model, as we say, we limit ourselves to spin 1. Mm-hmm. And the only massless spin 1 are the photon, and the photon is actually a stable particle. It cannot decay. Right? If you have spin of, particle of higher spin, like, some mesons, or baryons that can have indeed spin much larger than 1, those particles will decay. Okay, the decay also have to respect somehow Lorentz symmetry. So there are some selection rules that are associated to the decay of those heavy spin particles, but there is no problem. It's just that, again, there is no elementary particle of spin higher than 1, except maybe the graviton, but is not introduced yet in the standard model. Right?
But about the degrees of freedom will always be about eliminating one of them? We always have two degrees of freedom?
The counting is slightly different. For the graviton, for instance, spin 2, so 2s plus 1 is 5. Yeah. So that's a massive graviton will have 5 degrees of freedom, but the massless graviton has only 2.
Always 2. Okay. Two polarization.
Right. Massless spin 2 has only 2.
Okay.
Higher spin, I don't know. Yeah, probably there is some generic rule. So 2s plus 1 goes to something which is lower if the particle is massless. Mm-hmm. I don't remember now. We can check that.
Okay. And the other question is for curiosity, because why do we always choose the BEP to be in the lower component of the
It doesn't matter. This is totally arbitrary. No, you could put in the upper component, but then what you call electromagnetism wouldn't be this linear combination, you know.
Yeah, I guess you have to change the charges, but
Right. It's just a gauge choice, actually. You know, because at the end of the day, everything is SU2 invariant, so you can always do some SU2 transformation to bring the VAV to the lower component.
okay.
If you have some VAV in the upper and lower component, it's just a different SU2 gauge choice.
Okay.
It's just a convenient one, but
Yeah,
there is no physics there.
Yeah,
It's just a gauge choice. In the same way that when you are doing electromagnetism, sometimes you are using the Coulomb gauge, sometimes the Lorentz gauge, whatever. It's just
but
whatever is
that's
convenient
interesting.
for
No,
you.
everybody chooses, but always to be. Okay.
Here I've
Thank you.
tried to follow the usual convention, but
Okay, thank you.
More questions for Christophe?
what is really important is SU2 cross U1 down to U1 of electromagnetism. Right? This is independent of the gauge.
It's just kind of for curiosity because I know that in standard model it doesn't happen. But can I break the U1 with just one Higgs?
Now, I mean, with one X, the only thing that you can do is break SU2 cross U1 down to U1. With two X, 2X doublet model, in principle, you could break indeed SU2 cross U1 down to nothing.
Mm-hmm. Okay.
But with a single X doublet, you cannot do that.
Okay.
There is always one U1 that remains. I mean, you can see it here, right? If you have a doublet, again, by choice of SU2, you can always put the VAV into the lower component. And then, in this case, you have a U1 that remains unbroken.
Yeah, I mean, I think you can always rotate to this state, right?
It's SU2. I mean, by using SU2, you can always break the VAV. You can always bring the VAV into this form.
Mm-hmm.
And then it's obvious that this VAV leaves the U1 invariant. Right?
Yeah, okay. Thank you.
So if you want to break further down, you need to introduce more scalars.
So just make a comment. I don't know so much about superconductivity, but theoretical explanation is that the electromagnetic symmetry is broken. So basically the gauge is fixed. So it could be an example. But my question is other thing. I don't know if I am confused, but you said that the other Higgs degrees of freedom become the longitudinal modes.
Yes.
But I think it's strange because when you wrote the expressions for the new gauge bosons, it was just linear combinations of previous bosons. So how this is possible?
Well, again, it's a gauge choice, right? There is a gauge where the only degrees of freedom are the longitudinal component. The other component is the X doublet have been gauged away. You take, for instance, I don't know, this arc-C gauge, you send the C parameter to infinity, and then those degrees of freedom becomes infinitely massive. So they totally disappear from the spectrum. And the only degrees of freedom that are left are the longitudinal component of the gauge boson. So again, yeah, this might be confusing, but it's just working in the appropriate gauge.
Any further questions for Christophe?
That's the subtlety about gauge theories. It depends on the way you are looking at the various objects.
Okay, I don't see any hands up. So let's thank Christophe again.
Thanks.